Welcome to the debate. Today, we're tackling really the reigning champion of modern physics, the Standard Model of particle physics. Our source material frames this framework as the result of centuries of inquiry, really going all the way back to Galileo, yielding this single, incredibly powerful picture of how matter and, well, the forces of the universe are structured. The irony here, and this is really the focus of our discussion today, is that this theory is simultaneously hailed as, the most successful scientific theory of all time. And that's because of its almost, incomprehensible accuracy. It matches experimental results sometimes out to 9 decimal places. And yet, at the same time, it's explicitly defined by its profound incompleteness. It fundamentally fails to incorporate gravity, and it describes only about 5% of the universe's total known energy and mass. So, the central question for us is this.
Should the Standard Model primarily be viewed and perhaps taught as the pinnacle of current scientific achievement, a confirmed, successful framework that dictates the rules for all known visible matter? Or must be instead treated as a fundamentally incomplete structure whose glaring, frankly, enormous omissions have to define the future direction of physics? I personally believe quite firmly that the unparalleled triumph and confirmed accuracy of the Standard Model must remain our primary focus.
And I suppose I come at it from a fundamentally different angle. I absolutely respect the model's success. Who wouldn't? But its vast gaps, they're just too critical to simply gloss over. I'll be focusing on the model's fundamental limitations, arguing that its very success might actually be obscuring the deeper physical mysteries that physicists really need to urgently address if we're ever going to move forward.
Well, when we talk about triumph, we really have to grasp the sheer scope of this achievement. The Standard Model isn't just, a collection of successful results. It's an elegant theoretical architecture. It successfully categorizes and, crucially, unifies the 12 matter particles, the fermions, and describes how they interact through 3 fundamental forces. That's electromagnetism, the strong nuclear force, and the weak nuclear force. And all of these are mediated by the force-carrying bosons. The profound conceptual leap here, I think, is the mathematical unity. Every single one of these matter particles, every fermion, is described by the Dirac equation or a variant of it. This isn't just bookkeeping. This is finding a deep, shared sort of mathematical DNA for all reality's fundamental building blocks. And of course, the decades-long search culminating in the discovery of the Higgs boson really provided the capstone. It confirmed the mechanism.
Right, the symmetry breaking.
Exactly, the symmetry breaking mechanism, which allows particles to gain mass. This resolved a major mathematical inconsistency that, frankly, would have otherwise rendered the whole framework sort of incoherent. The Standard Model explains why the universe is the way it is, in extraordinary, confirmed detail.
That is certainly a powerful summary of its, let's say, descriptive power, but I think you might be missing the forest for the trees there. For all its mathematical beauty, the gaps are just too profound to simply label it the pinnacle. If we want to move beyond being glorified accountants of the observable universe, we have to look at what's missing. The source material states it very clearly. The model fails to explain a whopping 95% of the energy in the universe. That's dark matter and dark energy. Now, this isn't some minor tweak that's required. This means the Standard Model only describes a tiny, visible fraction of reality. If you had a map of the Earth that only showed Europe and nothing else, would you really call it the pinnacle of cartography? Probably not.
Furthermore, the model fails spectacularly on its own internal architecture, specifically the, seemingly arbitrary existence of 3 generations of particles and the completely mysterious pattern underlying particle masses. The Standard Model feels like a brilliant placeholder theory, incredibly successful only in its limited known domain. Okay, I see why you emphasize the gap. But I think you might be holding the model accountable for a task it was perhaps never designed to achieve. The model's success lies precisely in its ability to predict and describe everything we can experimentally observe in the known particle realm. The standard matter that makes up you, me, our planet, everything we see. That domain, the 12 fermions and the 3 forces, that's where it is truly unparalleled. It's true that dark matter and dark energy strongly suggest physics beyond the Standard Model. I don't think anyone disputes that. But defining the SM by what's missing, by physics we haven't yet discovered or understood feels a bit like criticizing, say, general relativity for not explaining stellar combustion back in the day. It's a different domain. We should celebrate its confirmed domain of applicability. If we define success by the questions we have answered with this unprecedented confirmed accuracy, then the SM really is the ultimate scientific achievement so far.
But hang on, you can't just cordon off 95% of reality and then claim complete success within the remaining 5%, simply because that 5% happens to interact conveniently with light. If the goal of physics, the ultimate goal, is to describe reality, then a theory that requires us to essentially invent completely new non-interacting particles like dark matter and this mysterious cosmological constant for dark energy, just to make the equations balance on a cosmic scale, well, that theory is almost by definition fundamentally inadequate. And the source material actually highlights this scientific dissatisfaction perfectly. Physicists are apparently so frustrated by the model's predictive success in its current domain that they are actively hoping they will find an experiment where it gives the wrong answer. Now, that sounds like the attitude of a field that recognizes the current structure is potentially a conceptual dead end for finding the vast majority of the universe. To achieve genuine unification, we can't just keep defining the boundaries to exclude our biggest mysteries. That missing 95% is arguably the most important data point we currently possess.
Okay, let's shift the focus slightly then to perhaps the most famous omission, the exclusion of gravity. You call this a critical conceptual flaw, and look, I agree that the lack of unification between quantum mechanics and gravity is the biggest challenge in fundamental physics today, no question. However, gravity is excluded from the standard model for, I'd argue, two entirely practical and justified reasons that don't necessarily diminish the SM success within its own sphere. First, gravity is just fantastically weak at the microscopic level. The source says it barely has any effect on a single subatomic particle. So its omission in particle colliders is empirically sound simply because its effects are utterly negligible compared to the strong and electromagnetic forces. In that sense, the SM is an accurate description of the quantum world where its forces dominate. And second, we already possess an incredibly successful separate theory for gravity, Einstein's general relativity. The problem is really one of reconciliation at extreme scales, like inside a black hole singularity or at the very moment of the Big Bang. It's not a total failure of description in their respective, largely distinct domains. We have ideas. We know the quantum nature of gravity likely involves particles called gravitons, and the theoretical framework for exploring that exists, even if actually detecting them experimentally is, well, far beyond current technology.
I'm sorry, but I just don't buy that it's simply a matter of it being a weak force or purely a technological limitation. I think you're minimizing the severity of the incompatibility issue here. The failure to include gravity isn't just leaving something out. It's a fundamental conceptual breakdown between general relativity, which describes space-time as smooth curvature, and quantum field theory, which describes point particles and forces within a fixed space-time. When we try to quantize gravity using the standard model's mathematical toolkit, the procedure called renormalization, which normally works beautifully to make quantum field theories predictive by canceling out infinities, it breaks down completely. It leads to uncontrollable infinities that are impossible to absorb or cancel. This demonstrates pretty starkly, I think, that the conceptual principles underpinning the standard model are fundamentally incompatible with the principles underpinning gravity. So when the source material says we have no idea how to peer into a black hole, it's precisely because our two greatest theories in physics fundamentally clash and break down at those high-energy limits. That's not just a missing piece. It's a deep sign that the SM's foundational mathematics is missing some critical unifying ingredient.
That's a fair articulation of the mathematical challenge, certainly. But let's maybe move inward for a moment, because even if we temporarily set aside these, let's call them external issues like dark matter and gravity, the standard model has deep conceptual mysteries regarding its own internal architecture. The mass problem, for instance, which you touched on earlier.
Yes, the mass problem. It's arguably physics' greatest unsolved puzzle within the standard model itself. As the source says, we have absolutely no idea
how to predict the specific particle masses. We can only measure them in experiments and then essentially feed those numbers into the model, like dialing in arbitrary constants. Why is the muon, for example, 200 times heavier than the electron? Why is the top quark nearly 350,000 times heavier? It's staggering. And these vast, seemingly random discrepancies are not solved by the Higgs mechanism. Let's be clear on that. The Higgs only explains how particles acquire mass through their interaction with the field, not why they acquire the specific, wildly different masses they do. If the model requires us to input, something like 18 arbitrary parameters, masses, coupling constants, mixing angles, derived solely from measurement, it really proves that the theory is merely describing the symptoms of particle interaction. It's not explaining the underlying root cause or the structure that governs these precise ratios. It acts like a phenomenal spreadsheet, incredibly accurate, but not a truly predictive framework from first principles.
That's a compelling argument against the SM being the ultimate theory, I grant you that. But I would argue that even this internal structure, these mysteries, contain clues of some profound underlying truth. While we certainly lack an explanation for the number of generations, why are there 3 copies? We do understand a key structural element. They must come in sets of 4 particles each, due to what's called a mathematical consistency condition in the standard model. This condition is known as anomaly cancellation. It's quite technical, but basically without the heavier quarks and leptons existing in these balanced pairs across the generations, the standard model equations would actually collapse and violate fundamental principles like conservation of charge. So the framework accounts for their necessary existence and correctly predicts their decay patterns. It provides the rigorous organizational tool necessary to even identify the mass hierarchy as the critical problem you're describing. So the SM doesn't just catalog these particles, it dictates the rules for their organization, even if the reason for the 3 repetitions remains admittedly a deep mystery.
But that organizational structure itself feels arbitrary, doesn't it? If the fundamental forces are truly meant to be unified, why do we need 3 essentially identical sets of matter particles that differ only by mass? It strongly suggests a deeper layer of dynamics, perhaps something spatial or some other symmetry that defines this progression from one generation to the next. The very fact that the model requires those 18 or so arbitrary constants, those external measurements plugged in, confirms, to me at least, that there is an underlying structure just waiting to be uncovered. A structure that the standard model merely hints at but cannot itself reveal. And that really leads directly to the path forward, doesn't it? The ultimate goal is presumably a theory of everything, unifying all forces, including gravity. But the standard model, at best, only hints at a possible grand unified theory, or GOT. The idea that the 3 non-gravitational forces, strong, weak, electromagnetic, might merge into one single force at extremely high energies. The source notes there are theoretical signs, like the way the force strengths seem to converge when extrapolated, but crucially, there is no experimental confirmation whatsoever of this unification. So the standard model seems to have stalled right at the point where we need to see the next layer of physics begin. It's almost too successful to fail in its domain, yet too incomplete to guide us clearly to the next step. We need to find new, perhaps exotic physics, maybe supersymmetry, maybe extra dimensions, maybe something else entirely, that can solve this mass hierarchy problem, explain the 3 generations, and incorporate the dark universe, all things which the standard model in its current form is utterly incapable of doing.
I'm not convinced by that characterization that it stalled, because I'd argue the SM's very successes provide the necessary clues for that next step. You call it stalled, I might call it the indispensable launchpad. The fact that the forces are described and categorized with such extraordinary mathematical precision is precisely what allows physicists to even conceptualize and rigorously pursue unification. The standard model gives us the precise mathematical framework for calculating where that unification point should potentially occur, guiding the energy levels needed for future accelerators or other experiments. Without this incredibly rigorous foundation, the 12 matter particles, the 3 forces, the precise mathematical rules governing their interactions, physicists would just be blindly guessing in the dark.
This foundation itself is the essential prerequisite that allows us to even begin conceptualizing what might lie beyond the standard model. It's not a stumbling block. I see it as the necessary roadmap for charting the unknown territory ahead. So, to summarize my perspective, the standard model remains a truly monumental triumph of mathematical unity and empirical accuracy. Its success in explaining all confirmed interactions in the particle realm is frankly unparalleled in the history of science. This profound, established framework provides the only rigorous foundation against all future theories, including any potential theory of everything, must necessarily be validated. Its achievement should be celebrated as the absolute pinnacle of 20th and indeed 21st century science to date.
And I suppose I come at it from a different way entirely. While undeniably accurate within its domain, the standard model's true scientific value, looking forward, lies less in its current descriptive power and more in the profound and inescapable questions it leaves unanswered. That massive 95% gap in our understanding of the universe's contents, the deep quantum gravity conflict, and the completely unexplained internal mass parameters, these mean it is fundamentally an incomplete framework. These omissions aren't really failures, perhaps, but rather crucial directional arrows, pointing physicists directly toward the next, absolutely essential layer of physical reality that we need to uncover.
And I think the source material clearly demonstrates that continuing this centuries-long journey, Galileo's journey as it were, requires a kind of dual approach. We absolutely must acknowledge the standard model's massive, confirmed achievement as a descriptive tool while simultaneously and diligently working to reveal the underlying structure that explains what currently remains a complete mystery. It seems we can only really move forward by understanding both the incredible height of our current success and the profound depth of our remaining ignorance.